In Math 20-1, our last topic is topic 9.3, quadratic inequalities in two variables. You can express a quadratic inequality in two variables in one of the following four forms. Y is going to be less than ax squared plus bx plus c. Y will be less than or equal to ax squared plus bx plus c. Y will be greater than ax squared plus bx plus c, or greater than or equal to ax squared plus bx plus c. Again, remember that a, b, and c are real numbers and that a cannot equal 0. Now, a quadratic inequality in two variables represents a region of the Cartesian plane with a parabola as the boundary. The graph of a quadratic inequality is the set of all the points x and y that are solutions to the inequality. Now, if we looked at y being less than or equal to x squared minus 2x minus 3, what would we do? We would graph y is equal to x squared minus 2x minus 3. And since we want to graph where it's going to be less than, we're going to shade in everything below that graph. That's our solution region. Now, we're going to look at a couple of different ones. If we said just less than x squared minus 2x minus 3, what we would shade in is we would not draw a solid line, but we would draw a dashed line, just like we did with the linear equations. We draw a dashed line, we'd shade in everything below it, because now that the points on the line are not part of the solution. The points on the line is where it's going to be equal to x squared minus 2x minus 3. So we only want the points that are going to be below that graph. Thirdly, where this is going to be just greater than x squared minus 2x minus 3, draw the same graph, again with the dotted lines, or dashed lines, sorry, and this time you're going to shade the region above it, which is just inside the graph. And lastly, if I said greater than or equal to x squared minus 2x minus 3, we're going to draw, again, a solid line and shade in the part above it. So those are the four different types of graphs that we're going to be drawing today. In example 1, it asks us to graph a quadratic inequality in two variables, with a being less than 0, a is negative. So graph y is less than negative 2 times x minus 3 squared plus 1. Well, when I look at this, notice that this is in the form of y equals a times x minus p squared plus q. That means that the vertex, since it's in our vertex form of our equation, is going to be at the point PQ. P, of course, is going to be, since it's minus P and minus 3, P is going to equal 3, and Q is going to be positive 1. So right away, I can say the vertex of our graph is going to be at x is 3, y is 1. Now I'm going to need a few more points to plot on here. So if I find two more points, let's say when x is 2. Well, when x is 2, and I plug it in, I'm going to find that y is going to equal negative 1. Now, since I have this point, and it's one off of our line of symmetry, x is equal to 3, I can say that the point 4, negative 1 must be another point on our graph, because that's going to be symmetrical, the same distance away from our vertex. So now I can draw our graph fairly closely. And it's going to look something like this. And so we're only graphing for y is less than, so whatever it is. So all we have to do is shade in the part below the graph, and we're finished. Now we're asked for part B to determine if the point 2, negative 4 is a solution. So notice that when x is 2 and y is negative 4, that point is in our shaded region, so it should be. So if we take our original graph of y is less than negative 2 times x minus 3 squared plus 1, and you plug in x being 2 and y being negative 4, we're going to say negative 4 is less than negative 2 times 2 minus 3 squared plus 1. And when you clean it up, you're going to get negative 4 is less than negative 1, which is true, and as correctly, it shows that it's back in that, it is in our solution region. In example 2, graph a quadratic inequality in two variables with a being greater than 0, a being positive. So now we're asked to graph where y is greater than or equal to x squared minus 4x minus 5. We're going to plot some points again to figure out where this is going to go. When x is 0, you'll notice that we get the point negative 5. So that's that point on our graph. When x is 2, 2 squared minus 8 minus 5 is negative 9. So it's that point on our graph. I'm going to have to extend my graph a little bit. Next point is going to be when x is 5. Hopefully it's going to be coming back up by then. 5 is going to be 25 minus 20 minus 5 at 0. So we'll have that point. And let's plot a few more. Let's say when x is going to be 3 and when x is going to be 4. Well, if you plug those two in, you're going to get negative 8 and negative 5. So plotting those points, I can see the shape of my parabola now. Let's do a couple more. How about when x is 1? When x is 1, I'm going to get a value of negative 8, so it's starting to look pretty symmetrical around the line x equals 2. Looks like that's going to be my line of symmetry. Doesn't matter really. But now when x is negative 1, I'm going to get a value of 0. I can pretty accurately draw my parabola. And when it says that y is greater than or equal to it, that means I'm shading in. I've got a solid line. I'm going to leave it as a solid line. And I'm going to shade in everything above it. Now I'm going to try 0, 0 as a test point, since that's probably the easiest point to work with. And when y is greater than or equal to x squared minus 4x minus 5, we got 0 is greater than negative 5, so yes, it's true, it works as a test point. In example 3, it asks us to determine the quadratic inequality that defines a solution region. So we're going to have to find our inequality this time. You can use a parabolic reflector to focus sound, light, or radio waves to a single point. That's what the guy's using in this picture. A parabolic microphone is a parabolic reflector attached that directs incoming sounds to the microphone. Rene, a journalist, is using a parabolic microphone as he covers the Francophone Summer Festival in Vancouver. Describe the region that Rene can cover with his microphone if the reflector has a width of 50 centimeters and a maximum depth of 15 centimeters. Well, let's draw a set of axes and then lay out our parabolic reflector. Remember, it has a width of 50, so it's going to go from positive 25 to negative 25, and it's going to have a maximum depth of 15, so it's going to start at 0, 0, and it's going to go up to 15 for a height. This would represent our parabolic reflector. We can also use this now to help develop an equation. Remember again our equation in vertex form, of a quadratic equation in vertex form. And we're going to start out with y is equal to a times x minus p squared plus q. Remember that pq are the coordinates of the vertex, and that xy is any point on the graph. Well, what do we know? We know that PQ is at 0, 0. So that tells me that there's the vertex, P must be 0, and Q must be 0. Now, I can find a positive point here because I know the point where x is 25 and y is 15 is also on my parabola. So I'm going to use x equals 25, y is equal to 15. I'm going to plug those four values into my quadratic equation and solve for a. A will be my last piece that I need to figure out in order to develop my quadratic equation. Remember this from chapter 3 and 4? I hope so. So here we go. We got 15 for y equals a, we don't know. X is 25 minus 0, which is just 25 squared, plus 0. Well, that's all we're done. So that'll be 15 is equal to 625 times a, dividing both sides by 625. A is 15 over 625, which reduces to 3 over 125. So now I'm going to plug a, p, and q back into my equation to say y must be greater than or equal to 3 over 125 x squared, but x is only going to exist between positive 25 and negative 25. Here's our last example. Interpret the graph of an inequality in a real-world application. Here we have quite a large equation, and Sammy and Jared want to learn the exhilarating sport of alpine rock climbing. They've enrolled in one of the summer camps. In a brochure, they come across an interesting fact about the manila rope that's used for rappelling down a cliff. It states that the rope can safely support a mass m in pounds. Modeled by the inequality, m has to be less than 1,450 times the diameter of the rope squared, where d is the diameter of the rope in inches. Graph the inequality to determine how the mass of the rope support is related to the diameter of the rope. So if you put this on, well, we only need positive values for d. We're going to put this in as y is less than or equal to 1450 x squared. Now we can put it into our calculator. These are some big numbers, so you're going to have to change your windows a lot. We really don't need the negative part, but if we just did the positive part, you can see that that's what it's going to look like. And here's 4,000, and there's the point 1.5 and 1,000. It asks on here, is the point 1.5, 1,000 means that a 1.5 inch diameter rope will support 1,000 pounds of weight. Your assignment for this section is page 496, numbers 1 to 10, and 13.